Hi everybody. Let me wind this down. Welcome back to Chem 121. I hope everybody had a good weekend. Nice and relaxing. I sure did, and then I stayed up way too late because insomnia is a thing. I have the wrong pad of paper out on my table here because I don't need a pad of paper at all. I need a tablet. There we go. Sorry, I had to sneeze there. I had to mute the mic real quick. All right, so let's see here. We're going to finish Chapter 6 today. We were working on this last week. We left off with balancing equations. Agenda items, since we're not done with Chapter 6, there hasn't been a Chapter 6 quiz yet, so that's probably going to go up today. But lab worksheet number 3 will be due tomorrow, I believe, looking at the calendar. The last call for that will be on Wednesday, so make sure you get it in when you can. Lab 2 has been graded. Generally speaking, I try to send fewer announcements out with, hey, I graded this, and anticipate that you will check your grade on your own whenever you want to. I do announce it in the Discord just because it's one sentence rather than sending you an email. And then I announce it in class. So hopefully that's enough avenues that people get the message that, like, hey, that's been graded. So you can go check your scores on that. Exams were 2 weeks ago, so we've already talked about that. Yeah, let's go ahead and get started here. Last week, I left these exercises on the screen for you to work on. I don't remember if I put the answers on the screen, but what I'm going to do is I'm going to work through a few of them, and then I will just give you all the remaining answers for them. So let's go on over here. We don't need that many on the screen at once, but let's just do 2 at a time. That'll work. All right, so here's our balanced equation. I'm going to try and do this so that the arrow is right in the middle. So iron and oxygen make iron 3 oxide. And we'll just put these little dashes here so that we can fill them with numbers. As you might recall, the first step is to take inventory. So we're going to just split this reaction arrow down the middle here. And we're going to count up the number of elements on each side. We're going to try and set them so that they're equal to each other. So on the left here, I've got iron and oxygen. And you should have the same elements on both sides of the equation. Otherwise, there's no hope of balancing it, right? If you suddenly have chlorine on the product side, but you didn't start with it, you're not going to make it somewhere. So double check that your equation is written correctly before doing this part. Otherwise, you just kind of get stuck right at the start. All right, how many iron do I have? Well, as written, I have 1. And how many oxygen do I have? As written, 2. And then over here, as written, I have 2 iron and 3 oxygen. And so the first question that we're going to have to address is, where do we start? Now, for a lot of students, the first move that they might do is they'd say, oh, I'll just do something like this, right? Because, hey, that helps me a little bit. And you can do this. However, it's not the best idea. So what I'm going to do is I'm going to actually back up here. What I am instead going to do is I'm going to introduce a strategy that helps out to solving these a little bit faster. And that is, where does the atom end up? What is its fate? So, for example, iron has to be present in iron oxide, right? And then oxygen also has to be present in iron oxide. And so what that means is that this oxygen right here and this oxygen right here are going to be related. And the numbers that you stick in front of these also have to be related, right? Because I got to get the same amount of oxygen on both sides. So if the left oxygens come in pairs and the right oxygens come in threes, can you put in numbers in the blanks so that you have the same amount? And the answer is yeah. I'll just do whatever the common denominator is, or common multiple, or whatever the correct term is. So if I have pairs of 2 and I have 3 pairs of those, that'll give me the same number as if I have 2 sets of 3, right? Because each of these will be 6. So 3 times 2 is 6, and 2 times 3 is 6. So that will balance oxygen by just looking at where it ends up. Now, a consequence of this is that the iron on the right side also changes, so this becomes 4. So you might be looking at that and going, oh, well, now I know what I need to put over here. I don't want to put a 2 on my iron. I got to put a 4 on my iron. And that's the correct answers. 4, 3, and 2. So if you're just starting to do these balanced equations and you're like, I have no idea where to begin, this is a really good consideration to apply to balance your equations in a manner that's more consistent with finding the end point. Because the starting point is kind of arbitrary. You could start wherever you want to. And really all roads lead to Rome in this sort of situation where everything that you do is going to get you to the answer. But there is an obvious starting point that is best. And when I say obvious, I mean maybe not necessarily intuitive, but optimal. Optimal is the word I should have said. Not obvious, but optimal. All right, let's do another one and see if we can show that concept in action again. So we'll look at mercury oxide decomposes into mercury. Oh, so where'd my arrow go? There it is. That's a little too close. And then I threw the mouse on the floor. Let's fix that. There we go. We'll do the same thing. We'll start with the same setup. And let's do the same thing. Where do all the oxygens have to end up? Well, they have to end up over here, right? Where do all the mercuries end up? Well, they have to end up right here, right? So whatever number I put in this spot, I have to put the same number in this spot. There's just no way around that, right? I can't have a 3HGO becomes 2 mercury. That can't happen. And then also, whatever number we put in the mercury spot over here is probably going to be half of the number that we put in for oxygen. So what if I just put a 2 here and a 1 here? That'll get me oxygen, right? That's all set. It also increases my mercury. And then I fix that by just doing this. And you're all done. So try and identify where your elements are going to go. And you should be able to do this no problem. All right. We're going to do these last 2 here. There are 2 more. I'm just going to write the answers in a second here. But in the interest of time, I don't want to spend forever on this. All right. So this process that I'm writing down here is how we mine up iron. What we do is we mine up iron, which is rust, Fe2O3, because all of the iron in the earth has oxidized with ambient oxygen. Ambient, not necessarily in the air, but in like other places, so like in other types of ore itself or whatever. And in order to get it back to iron, we have to reduce it. We have to give it a reducing agent, and we use carbon for that. So the carbon takes the oxygen instead, and we get the iron. That is a little bit of metallurgy for you, just in case you were curious. I find metallurgy fascinating. If I could go back and do it again, I would study, like, that sort of chemistry, I think. Just like, hey, this is what minerals do. This is how they form. I think geology is really cool. All right, let's tally everything up real quick. So it should be very trivial to count these, but just be careful. All right. Now, using the hints that I said before, we want to start with the complicated stuff first. So this looks like the most complicated thing. Can I connect it to a simple thing or a different complicated thing? Well, the iron is simple, so that one's just going to shake out when we're done with it, right? But what about the oxygen? This is kind of tied up in something too. So I would start with the iron oxide and the CO2. And just like before, we have something that comes in threes and something that comes in twos. So we'll just swap the numbers here so that this happens, right? And then once you've done that, everything else sort of falls into place here. So first I gotta calculate my iron. So 2 pairs of 2 is 4. Over here I have 3 carbon. And now I can just clean up, right? So here I could just do that. And here I can just do that. Now, you may be watching this and being like, gosh, Wes, this is so much easier. Why didn't you tell us this before? And really the answer is we ran out of time. So hopefully looking at this over the weekend, you were like, wow, these kind of suck. I hope there's a better way and that Wes is going to say something. And then here we are on Monday. We'll do one more. Because balancing equations can kind of suck if there is not a very obvious first step for you to follow. You'll notice I'm not writing the phases in because we don't care about the phases for balancing. So you don't need to write those. The phases will be important later on, so don't forget that they exist. All right. Now I got to sort out all of this stuff here. You might remember that I said to keep polyatomic ions included. You don't have to worry about their charges, assuming that all these ionic compounds that I've written out are correct, which they are. But if I just keep my PO4s written as PO4s, then what I can do is inventory them a little bit easier as opposed to writing out P's and O's. In this specific example, if you did P's and O's by themselves, it would be okay. It would work out fine. There are some examples later in chemistry, though, that if you have to balance them and you see polyatomic ions and there's extra oxygens in there, doing the separation can actually save you so much time. So how many sodium do I have? I have 3 of them. I have 1 phosphate, a magnesium, and 2 chlorine. And then over here I have 1 sodium and 1 chlorine, 3 magnesium, and 2 phosphate. And nothing is balanced. Everything is terrible. We need to fix this somehow. And again, look for the most complicated thing. In my opinion, that's this. So with that in mind, the magnesium has to come from here. So that number is going to be related to it. And the phosphate has to come from here. So that number's got to be related to it, right? Okay. Well, how many phosphate are there? There's 2, so I'm just going to put a 2 there so that this works out. As a consequence of that, I get this. Because 2 times 3 is 6 for my sodium. And then we'll work on our magnesium here. I have 3 magnesiums. They had to come from this, so I'm just going to stick a 3 here. And my chlorine changes as a result because 3 times the 2 that are right there. And then finally, I need to balance. Well, let's see here. So this one's good. This one's good. But I only have 1 sodium and 1 chlorine. I need 6 of them. So I'll just do that. And you're all set. Now, if you're watching these and you're like, man, these sort of just solve themselves at the end, the answer to that question is, yeah, they do. That's how these equations work, because everything is linked together, right? So it's kind of impossible for you to end up in a situation, if you're following this sort of strategy, where you get to the last thing and there's nothing you could do. Like, you can't balance it. The exception to that would be you made a counting error, or you have multiple sources of a given element. Like if I have oxygen that starts in O2 and then ends up in multiple products, then that gets a little dicier. These are more straightforward examples. But hopefully that has given you some insight into a better way to do these. So I've written down all those. I think there's another equation, isn't there? No, there's not. I'm going to just quickly write down the answer to this last one. I can get my pen out. Why did that disappear? I don't know. Why does this program do anything? Who knows? There we go. Same sort of strategy. I looked for the most complicated thing. That was this one. So I said, okay, how many chlorine are there? Well, the only place that chlorine shows up is that, so I just have those numbers reversed so that it multiplies out. And then leave the simplest ones for last. That would have been aluminum and chlorine. Or, sorry, aluminum and copper. All right, so now that you know how to balance an equation, we're going to use that immediately. With all the stuff that we talked about for Chapter 6 last week. Remember how we were turning grams into moles? And then into moles of something else, and then into grams of something else? And the way that we did that was to do something like this. So we used P2O5 as our example, and we said, okay, in 1 mole of P2O5, so one of the big thing, how many moles of oxygen were there? We said 5 because the subscript told us that. What we're going to do today is we're going to look at a chemical equation and do the same thing. So this is the Haber process. This is how we make ammonia for fertilizer. You take nitrogen from the air and hydrogen gas, and you heat the hell out of them at really high pressure, and you make a small amount of ammonia. And when I say small amount, I mean like 30% of the reaction will react. You then distill that off or remove it through some sort of separation method, and then the reaction will continue, and you can isolate the ammonia, sorry, and send it along its way for fertilizer synthesis. Ammonia is used in all sorts of things. It's a very important compound. If I read this reaction as written, what it is saying is that in a reaction with 1 molecule of N2 and 3 molecules of H2, I will react those to get 2 molecules of NH3. So in other words, if I was to compare these sentences together and make statements that were mathematically true, I would say 1 molecule of N2 reacts with 3 molecules of H2. Or I could say both of those, or either of those, will eventually form 2 molecules of NH3. Now, it's hard to work with this double equals thing, where I have A equals B equals C, right? So, at any given time, we're just going to work with 2 things, and then ignore the other one. So, in all of our questions that we're going to be doing in this section, I'm going to ask you about 1 molecule that is given to you in terms of an amount, and I'm going to say, what does this other thing do? How much of it is made in some capacity? So that would either be like molecules, moles, or grams. And you're going to just ignore everything else. Because even though it's equal, we can really only compare 2 things at once, right? So that's what we're going to do for this section. We're going to compare these things together. Now, of course, working in molecules is not super helpful. So what we're going to instead do is we're going to multiply by moles. And then do the comparison. So 1 mole of nitrogen would react with 3 moles of hydrogen. Or 1 mole of nitrogen would eventually produce 2 moles of ammonia, given adequate other reactants. So what do those equations look like when we write them all out? So that's going to look like this. Here are all the equations that you could possibly write for this reaction. And to do that, I'm just pairing any two together. So here's the first one that we wrote right here. But you could pair any two together that you want to. And your job for a problem is going to be to identify which pairing do you need to solve it. And then once you have that pairing, you're going to use it in your chemical calculation. I almost said stoichiometry and realized you guys don't know what that word means. This process is called stoichiometry. Not sure if the online text or the textbook has that, but does my reaction not show up on this slide? Hold on. It doesn't. Interesting. Okay. Let's just write it out again real quick. That's the wrong number I wrote. Wrote the wrong thing. Let's fix that. All right. We do need this equation. So impossible to answer the question without the balanced equation. So that's an important starting point. Now what we need to do is we need to read the problem and ask what it's telling us, because we're going to see these problems like we did in the previous section where we were doing grams to moles of a big molecule and then was looking at a part of it. So here's what the question is asking. It's asking us 5 grams of nitrogen is reacted with an excess amount of hydrogen. How many grams of NH3 are made? Now, you probably also noticed here that the third thing is included, but the amount is not shown. It's just written as excess. That color is real dark. I did not expect it to be that dark, so we're going to just... Let's do light green here. We're going to highlight it in a different color. There's a cat here. You might actually hear him. There we go. Whenever you see the word excess, what that means is that you're never going to run out of it, and so you have it in abundant supply. So ignore it for this calculation, because it's not going to determine how much stuff you can make, because you have as much of it as you need. So for any given problem that you see in this class, specifically this class, 121, if you see the word excess, just take your pen and strike through that substance, because it's not going to help you. You have to put in hydrogen for the reaction to go, because you can't make ammonia without hydrogen. And what the word excess means is that, hey, I'm going to give you as much as you need. No more, no less. But it's not going to affect your result. The things that will affect your result are the other substances. So we have 5 grams of nitrogen, and I need grams of NH3. And so you probably remember this from last time. So A is nitrogen, and B is NH3. And I started here, and I'm going here. So you're going to do this sort of calculation. That gets you around the bend here to get to the target. All right, let's do that. So we'll go back over here. Oh, I do need the top part. There we go. Okay. So our strategy for this would have been grams of A, which A was nitrogen. Then we turn that into moles. Then we'll do moles of the other thing. And then we turn that into grams. And so this is just going to be all of the calculations that you did on Tuesday and Monday. So we'll set up the units so that they cancel out. And then we have to fill in those numbers. How many grams of nitrogen are in a mole? Hope you remember which website to use. Just in case you don't, here it is. Boop. There you go. So how many grams are there per mole of N2? So if I type in N2, it will tell me the answer, and this is 28.01. You could just take the number on the periodic table for nitrogen and times it by 2. All right. Now we have to do moles of NH2, or not moles of NH2. I don't even know what the hell that is. Moles of N2 and moles of NH3. How the heck do we get this relationship? Well, if you look up at the balanced equation up there at the top, you'll notice that I have moles of N2 and moles of NH3. So for every one of those, I make 2 of those. So let's go incorporate that into my expression. For every 1 and 2 I put in the reaction, I get 2 NH3 out. And so this step is just like before where you were saying, okay, how many in the big thing, how many of the little thing that's within it? And you pull the numbers out of the subscripts. Here you use coefficients instead from the balanced chemical equation. So we'll even notate that. So these numbers right here are the coefficients from the balanced equation. All right, and then the last thing that we have to do is we have to do this. We have to turn our moles back into grams. How many grams of ammonia are in a mole? We can go to Lentech to do that, or you can use your periodic table and just sum all the numbers together. 17.03. And then finally, we got to use our calculator to multiply all the numbers together. So that is 5 times 2 times 17.03 divided by 28.01 and a bunch of ones. And I get 6.08 grams of ammonia. Last thing we should do, how many sig figs? These two numbers are counted, and so have infinite sig figs because they are exact. This one is 4. Basically, look for all your decimal numbers in here. Those are going to be the ones that are sig figs. Unless I give you a number at the start that isn't a decimal. Numbers you are given to start are always written to the correct number of sig figs that are intended. So if you see me write 74 grams, that's intended to be 2 sig figs. All right, so we've seen how to do a basic stoichiometry problem. I didn't click over here. There we go. So now I want you to do the same thing. Now, unfortunately, my slides don't have the reaction on here for some reason. And I've already screwed it up. Look at me. Woohoo. What I want you to do is I want you to try this problem because it's virtually the same problem that we just did. Okay, so I have balanced the equation for you. And so the statement is 2.75 grams of hydrogen are going to be used to make ammonia. How much N2 is needed in grams? So you'll notice that I use the words make ammonia. That's just telling you that that's its purpose. But the problem doesn't involve ammonia, right? We're just using it to make ammonia. So you could scribble out ammonia, draw a line through it. We're not going to work with that part of the equation. We're going to work with nitrogen and hydrogen. And I'm giving you a starting amount of hydrogen. So from there, do the calculation to determine the amount of nitrogen in grams that you need. Same process that we just did. I'll leave you about 5 or 6 minutes to try this while I go clean my glasses because they're just disgusting. I can't see anything. So I will be right back. All right, one more minute. We'll go over the answers here. All right, let's go over the solution to this problem, which we'll go over here. I'm clicking on the wrong monitor. There we go. All right, so to blueprint out our path here. Oh, I guess I didn't actually do that on this screen, so let's go back over here real quick. And so what we're going to do is we're given a grams of hydrogen, so we're going to start here. We need to figure out how much N2 is needed in grams, so we're going to end here. And we're going to do this same process to solve. And so we'll write that out. So we're going to do grams of what we're starting with, so that's hydrogen. Turn that into moles. Turn it into moles of the other thing. And grams of the other thing. You'll notice that this is going to be a pattern that we follow a lot. And if you need to have a reference for this to memorize, another instructor that teaches 121 came up with Gamolmiga. It just sounds stupid enough that you might remember it. And what we're doing here is Gamolmiga. Turn it from Gamol to Molga. Gamolmiga. And if you say it enough times, it will still sound stupid. But some students have claimed, like, hey, that's a catchy enough thing that I can remember what it is, so. Anything that helps you guys. All right, we're going to turn our grams of hydrogen into moles of hydrogen. And according to the periodic table and or Lentech, 1 mole of hydrogen is 2 something. Let me just get the exact number here. 2.018. Sorry, it's not exact. It's approximate, but more sig figs than just 1 digit. There we go. Moles H2 and moles N2. How do I figure this out? Well, we go to the balanced chemical equation that I have written on the... Oh, no. I didn't realize that I hadn't clicked over here. You know, let's just do this all again. There we go. We'll do it again so you can actually see it. All right, so let's start with the amount that we had here. And so we looked this up on Lentech, and it was 2.016, actually. I wrote down the wrong number. There you go. And then for this relationship, we just use the balanced chemical equation up above there. So I have, for every 1 N2 I put in, I also have to put in 3 H2. So just match up the numbers from the balanced equation. And then how many grams are in a mole of N2? This is not mole per N2. This is me crossing it out. And according to Lentech, that is 28.02. That should be the same number as you got before. Could be 28.01. I'm trying to do it from memory. What did we write down before? We wrote 28.01. Okay. And I'm going to punch all that in the calculator. Notice that you have two numbers on the bottom when you're dividing. Make sure you use parentheses here. So 2.75 times 28.01 divided by parentheses 2.016 times 3. Close parentheses. Should get 12.7 when you're done. So if I put in 2.75 grams of hydrogen gas, I also had to put in 12.7 grams of nitrogen so that they all react completely. So that's what this problem is saying. All right, I have 12.8 here, probably because I had a rounding issue with using different numbers from different sources. It's fine. All right, I'm going to give you this reaction, and what I want you to do here is I want you to tell me what mass of sodium azide would decompose to create 253 million molecules of nitrogen. Now, this seems like a really big number. This is a lot of molecules, right? But keep in mind how many molecules are in 1 mole, and then how many grams are in 1 mole of that. So what we're asking for here is how much of this would make this known amount. So you're going to start with a number you know. And so we'll say A is nitrogen, because I know what that one is. And then B is sodium azide, because that's the one I'm solving for. What mass? So this is your goal, and this is where you're starting. Same type of problem, but you're going to start with a different number. All right? I'm going to give you a few minutes to try this, like 5 or so. We'll go over the answers in just a bit. Then we'll take our break. One more minute, we'll go over the answer here. All right, let's go over the solution here. All right, so we're going to do a similar sort of calculation here. It's just that instead of starting with a mass, we're going to start with a number of particles. And that number is going to be 253 million, which is 2.53 times 10 to the 8 molecules of N2. I can easily convert that into moles. And once I know the number of moles of N2, we can go to moles of the other reactant, which is NaN3, which we can then turn into grams. Kind of ran out of space here, but that's okay. Sorry, I heard my cat meow, and now I'm trying to find him, but I don't see him. He's just being a doof. All right, how many molecules are in a mole? Hopefully you immediately are saying, oh yeah, Avogadro's number of them, huh? All right, now that I know the number of moles of N2, we can turn moles of N2 into moles of sodium azide, which according to the balanced equation would be for every 3 N2 I put in there, or for every 3 N2 I get out, I need to put in 2 NaN3. And then finally, we turn grams into moles, and you've done that before. You just go over to Lentech and type it in, NaN3. 65.01. And then we calculate the solution. 2.53 times 10 to the 8 times 1 times 2 times 65.01 divided by parentheses Avogadro's number times 3. And I get this extremely tiny number . Oops. And you might be thinking, how the heck can I get a number that small? That's like not even like nanograms. That's like less than picograms. That is such a small mass. How can that be the right answer? And it turns out it is the right answer because this is not a very large number of molecules. Remember, you need this many times 10 to the 23 to get a mole, which would be like a few grams. I have 15 orders of magnitude smaller than that. So my answer is going to be about 15 orders of magnitude smaller than a gram. And it is. It totally is. So if we go back over here, you can see that. All right, I'm going to leave these problems on the screen in case you want to try them. Real quick, we'll do these when we get back from the break, but for now, we are going to take our break because we're due for one. So let me turn the music back on here. Take a 10-minute break, go get some water, go pet a cat, chill out to the Zelda Wave music, which hopefully we haven't used yet this quarter. I was scrambling to think of something. And we'll see you in just a bit. Probably can barely hear me there. There we go. Let me turn this down a little bit. Alright, what I want you to do is work on this problem. Notice that my equation up above isn't necessarily balanced because I don't have any numbers in there. Double check to see if they're all ones. Hint, they're not. And if you have to, hint you will, balance the equation before doing this these problems. So the first problem, I'm going to give you 0.522 grams of KClO3. And what I want you to do is tell me how many grams of KCl will be left after I let all the grams of KClO3 react. Then I want you to do the same problem, but instead of solving for KCl, solve for oxygen. And then finally, look at the numbers that you got and tell me, does the conservation of mass check out from the numbers that you calculate? And it should, because we know that you cannot create or destroy matter in a balanced equation, right? So go ahead and try these. I'm only going to give you about 6 minutes to do this because I do want to do some chapter 7 today. So do the first one if you can, and we'll go over the answers in just a bit. Post your answers in the chat as you get them, just so I know where people are at. Let's do one more minute. We'll go over the answers here. All right, let's go over the solution here. So the first thing that we need to do is balance the equation. So I'm going to just leave that at the top here. And what we'll do is I'm going to go in and fill in the solution here for the balanced equation. And hopefully you looked at this and said, oh, well, if I do this and this and this, it becomes balanced. That should be pretty quick to do. And then what we're going to do is we are going to start with our 0.522 grams. And let's make our little blueprint here. So grams KCl3, which we're going to turn into moles. And then once we've got that, the goal of the problem is to get grams of KCl here. So if we turn moles of KCl3 into moles KCl, we can then do that. There's our gamomega. And then how many grams are in a mole of KCl3? Let's go to Lentech and calculate that. 12255 is what I calculate. And then we've got moles of KCl3 and moles of KCl, because I'm going to convert from moles of something to moles of something else. Using our balanced chemical equation at the top there, what numbers do I put that where? So every 2 KClO3 I put in the reaction, I get 2 KCl out. You may think, well, that's silly. I'm just going to put whatever I get in, or whatever I put in, is whatever I get out. Yeah, that's because the 2's are the same number. In fact, 2 divided by 2 is just 1, so these numbers cancel too. But that is designed correctly. And then finally, grams per mole of KCl. We'll just go back to Lintech, and I'll just go delete, enter. 74.55. So let's punch that all in the calculator. 0.522 times 2 times 74.55 divided by 12255 times 2. And if you don't include the 2's in there because you cancel them, totally fine. All right, there's the mass of KCl that I got. Now, we could do the same problem again. And instead of grams of KCl this time, we'll get grams of O2. And so this is all going to be exactly the same for the first few steps. And then when I get to this part, we're just going to do moles of O2 instead. So still 2 of these, but now I have 3 of those because there's a 3 for my oxygen. And then this last part here, how many grams of O2 are there in a mole? And I go to Lentech, and I got 32.00. So how many grams of oxygen are there? 0.522 times 3 times 32 divided by 122.55 times 2. And I get this. And now you might be asking, okay, how do I verify the conservation of mass? Actually, let's do this in a different color. And the answer is, well, the mass should be equal on both sides, right? So what did I start with? I started with that many grams, and this should equal whatever the products were. So one product was 0.318 grams, and the other was 0.204 grams. And if you punch that in your calculator to that number of significant figures, lo and behold, that's what you get. So that verifies that the conservation of mass was followed for this problem, and in fact, for any chemical equation, it is followed. All right. That's chapter 6. Chapter 6 is kind of the hell chapter. It's behind us now, so write down the homework practice down here at the bottom. Oops, there we go. I'm trying to do that with the mouse because I'm about to click forward. And then the last thing you have to do is celebrate. Because it's all done. Hooray! Alright, give me a second to get chapter 7 on the screen here, because I have to fish around for it in a folder. Folder that I closed, apparently, unless it's over here. What is over here? Alright, let's do some chapter 7. Chapter 7 is about different phases of matter. We're going to primarily work with gases for today, and then afterward we're going to talk about the other phases, how you change between them, primarily liquid and gas. I'm drinking my water there real quick. And then at the end there, you're going to see that there's one section that's by itself. That's actually the meat of the chapter, Intermolecular Forces. Intermolecular Forces might be the most important conceptual thing for this entire class, because when you get to biology, and I want to say it's 211, cell bio, major cellular, they're going to talk about intermolecular forces a lot, and you're going to be expected to know what the forces are that hold molecules together, because obviously there are things that hold molecules together, right? We aren't just like this blob of matter that continually expands. Like, cells hold themselves together somehow. There is a mechanism by which they do that, and it's not just, oh, they have a cell membrane. Well, what holds the membrane together? Turns out it's intermolecular forces. To understand intermolecular forces, though, we have to talk about phases in a little more detail. And I guess because there's nowhere else in the text where it makes sense to do it, we talk about gases here. So that's where we're going to start. What we're going to do is we're first going to define matter in terms of motion and energy. And the reason that we're going to do this is because gas particles are in continuous motion all the time. So take a deep breath, for instance. And then what I want you to do is exhale slowly. Kind of like you're doing yoga. And then I want you to imagine when you breathe and the air is coming out of your nostrils or your mouth or however you're exhaling, do the particles just stop and then fall to the ground? Or do they just kind of leave and then bounce around all over the place? And you probably already know the answer to this. Well, they just kind of go everywhere, right? If you opened a bottle of, like, say, Pine Sol or kitchen cleaner, something that's very strong in terms of odor, like an air freshener, something like that, and you opened it on one side of the room and then you moved to the other side of the room, you would eventually smell it despite it being so far away. And that's because the particles of the freshener disperse into the air, bounce around all over the place, and eventually fill the room. Where does that motion come from? Well, it comes from things like wind and temperature, right? So wind is just air pressure moving around over the surface of the Earth. And the temperature is just heat. Things that are hotter have energy in them, right? That energy makes things move, which is why particles are able to move at room temperature. They have energy. Even when it's cold out, particles have energy. They just don't have as much energy. And so when you are exposed to the cold, particles that hit you don't have enough energy to keep your body from losing temperature. There's all sorts of crazy thermodynamics things I could talk about. But suffice it to say is that the energy in a particle that is moving is called kinetic energy. It is the energy of motion. Now, there is a different type of energy that is also available, and that's called potential energy. Potential energy is energy that you can potentially get by doing something. For instance, if you have an object on your desk and it is perched precariously on the edge, and maybe you bonk it with your elbow, if it is not sitting on the table or desk anymore, it's not going to just float in space and have no energy or no motion, right? Instead, what it happens is it hurtles to the ground and makes a big thump. For example, like this, which hopefully you could hear. I dropped my calculator on the floor, and then it hit the heater, and then I was like, oh shoot, I should have watched where I was dropping that. When something drops to the floor, it starts in a stationary position, right? So if this is my table here, we'll draw a little sketch of this. So if this is my table and here's my object, then what ends up happening is my object starts off going real slow, and it accelerates as it hits the ground, right? In other words, it must have had energy. We call that potential energy. Because it had the energy from where it was in space, by virtue of it being on the table. If you put it on the floor, it's not going to fall further, so there's no potential for it to fall and turn that energy into an impact. You put potential energy into things when you lift them. That's why they're heavy. You are expending your energy to give it to the object when you put it on a shelf. If the object falls off the shelf for whatever reason, the energy that you gave it is then expended as it falls, and it accelerates towards the Earth. This is why lifting things is a method of working out. We're expending our energy to give some heavy object potential energy, and then we let the object drop, or we ease it down on the floor so we don't damage the floor. So potential energy is energy that something can have based on where it is relative to other things. Those relative places can be height, or in chemistry, those could be things like interactions, like bonds. So like an ionic compound has high potential energy because all of the atoms are held together in bonds. If I were to release those bonds, the atoms would have very high energy, right? All right. Now let's talk about the ability of things to move when they have high energy. If something has high kinetic energy, because kinetic energy is the energy of motion, things must move very quickly. If something has a high potential energy, though, it must not move at all. Because if I give something a high potential energy and it starts moving, that means it's going to be moving towards a low potential energy. In other words, the floor, right? So high kinetic energy is lots of motion, whereas high potential energy means stationary. So our logic makes sense. Something has high potential energy as long as it stays there in that position. And so what we're going to do is we're going to define the phases of matter based on potential and kinetic energy. So the first shape that we're going to define, or the first state, I should say, is the solid. Solids have high potential energy. And because the atoms or molecules in a solid are essentially stationary, their potential energy must be very high relative to their kinetic energy. What about a gas? A gas is the opposite. So gases expand pretty much in all directions as far as they can. So their kinetic energy is very high, and particles move very, very quickly. So those are our two extremes. Solids, the molecules are stationary. Gases, the molecules move around a lot. Only gases have the high kinetic energy state. Solids have the low kinetic energy state. They have a high potential energy state instead. Now, what about a liquid? Liquids are kind of in the middle. Liquids have both. So molecules are close together, so they are held together and restrained in some way. They can't go sailing apart, because that would be a gas. However, the molecules in liquids move. You can see this in action by adding food coloring to water. If you add a drop of food coloring at the surface, what ends up happening is the molecules of food coloring, which you can generally see because it's a dye, will slowly disperse throughout the container. And this is due to the random motion of molecules. They're just going to move in all directions however they get bonked about. Whereas with a solid, if you put a drop of food coloring on a solid, and it's a solid that isn't permeable, you're not going to see this spread through the solid in any appreciable amount of time. So those are our three states of matter and how we've defined them with regards to potential energy and kinetic energy. And so there's a few homework practice problems that deal with this sort of concept. And we're going to use this as a basis for talking about gases, because really what we care about here is gas particles move. How do they move? They tend to travel in straight lines until they bonk into another particle, in which case they collide and go in a random direction. This is why you can smell stuff if you open something in a bottle that's really pungent and then go to another room. Because smells and stuff can travel around corners. They don't just travel in straight lines and bounce randomly. They bounce off of other particles, and eventually whatever odor you are observing can be observed from any location in your house or apartment or whatever. So that's going to be our basis for gases, is particles move and bounce around. With that idea in mind, What I want you to do is I want you to imagine a gas. And so I'm going to draw a gas on the screen. I'm actually going to give you a few seconds to think about this. I lost my cursor. Hold on. Where did it go? There it is. Oh, no, that's weird. Why did it disappear? Oh, I see what's going on. I was holding the pen over the tablet. If I hold the pen and it's too close to the tablet surface, no matter what I'm doing with the mouse, the cursor goes back to the tablet screen. All right, so I'm going to drop a container. And in my container are going to be a bunch of gas particles. Now, there's going to be way more than this in any gas particle or any gas sample. And like we said, the molecules are moving around the container, and they bounce off each other. And they just do whatever it is that they want to do for the day. And there we go. So I just have a random assortment of molecules. They're all moving about. And I want you to try and think of 4 different things that you could measure about the gases in this container. You could type them out if you want, but I just want to give you a little opportunity to have a little thought experiment here, okay? So I'm going to go quickly just grab more water. And when we come back, we'll discuss what your thoughts are. All right, back in a bit. All right, sorry about that. I'm dehydrated, so I have to keep drinking water. All right, so we have some ideas written in the chat. All right, so let's look at those. So the first one that we can measure is what are the dimensions that the gas is constrained in? Because if I drew these dimensions in any other size, that would affect the gas itself, right? And so that would be the volume. So we're going to give it a variable. When the particles collide with the side of the container, these impacts are called pressure. Pressure is a little bit nebulous to define until we look at the kinetic molecular theory, which is the theory that molecules move. What is the pressure that you feel? And the answer is, it's all the molecules simultaneously bouncing off of your skin or your eardrum or whatever. If you have ever gone flying, you've probably experienced changes in pressure. We're going to draw a picture of that in just a second when we talk about pressure. But suffice it to say, the more collisions there are on a surface, the higher the pressure. Likewise, if those collisions are occurring at a faster speed, they'll exert more pressure too. Now, there are other things that we can measure. For instance, how fast the molecules are moving. Now, if these were vehicles, we would use a speedometer. But for molecules, we use a thermometer. A thermometer is just a speedometer for molecules. This is called temperature. Believe it or not, a thermometer is just how fast molecules are going. We have assigned that a number. And that number is in Fahrenheit or Celsius. If the molecules can't move, then we measure how quickly they vibrate. So for solids and such that are rigid, you can measure a temperature. But for gases, temperature is defined as how quickly something is moving. Now, there are other factors in mind, so like the mass of the molecule does come into play. More specifically, temperature is how much kinetic energy something has. But we're going to extrapolate that to velocity for our purposes, because we're going to assume that the identity of the gas we're looking at doesn't change, and so we could just not worry about that. The last thing that we can measure is the quantity of the gas inside, and we're just going to say number for that. Sorry, I had to sneeze again. Whew. I think it's cat dander. I was brushing my cat during the break here. All right. We have measured 4 properties of gases that are practical for us to explore. And so what we're going to do is we're going to put all of those variables together to make equations, but we're not going to do that just yet. So there's our 4 variables. I'm going to write these letters down next to them just so you remember them, because these letters are going to come back in our equation. So pressure is P, volume is V, temperature is T, and the number is lowercase n. There's a reason it's lowercase. We're not going to get to that in this class, though. Let's talk about pressure a little bit more. Where does pressure come from around us? Why is there this force pushing us inward by particles? And the answer is it's due to gravity. Since gases are matter, and all matter is attracted to other matter, gases must be also attracted to the matter of the Earth, and therefore they are subject to gravity. They are pulled in the downward direction. On the screen here, you could see that if I have a square meter that I just sort of extend all the way up to the edge of space, so the end of the atmosphere, where space begins and the atmosphere stops, and I draw that straight down, what I end up getting is a mass of air that is roughly 10,000 kilograms. That mass of air is pushing down upon you and everything in that square meter. So if somebody ever asks you, hey, do you even lift, bro? You can say, sure. I lift this much every second. 10,000 kilograms. It's not impressive, though, because everybody can do this. that force being applied onto the ground in your skin and your ears is called atmospheric pressure. And so this is the force of pressure that you feel at ground level. Now, what if you aren't on the ground? What if you are like in the air, or you even change elevation, or you're underwater, or things like this? We're going to just keep this picture here for now. And let's draw a little diagram here. So I'm going to, this is the Earth. And so on the Earth, I have this mountain here. And then maybe we have the ocean over here. And then up here will be the edge of the atmosphere. And then up here would be space. All right. This diagram is obviously not drawn to scale because you could fly like 40,000 feet up and there's still atmosphere there. But no mountain is 40,000 feet tall on Earth. All right. Let's suppose that you are right here at sea level. So here is you. Here you are. And the force of air pushing down upon you would be this much. So the pressure from the air here would be equal to 1 atmosphere. And this is because we define 1 atmosphere of pressure at sea level. So you have to be at sea level. Don't ask what happens when global warming makes sea level go up. How does that change pressure? I don't know. I don't know how do we redefine it? I don't know. But the colloquial definition is that at sea level, you have 1 atm of pressure. Now, let's suppose you weren't in sea level. Let's suppose that you lived in Denver. Denver, Colorado is known as the Mile High City. Because the elevation of the city is about 5,280 feet or whatever. If I were to measure the pressure that you feel in Denver, well, you can easily see, I mean, just by virtue of, look at what I'm going to do. I'm going to take this, and you can see that, wow, that's way shorter, right? That's a lot less air pushing down on you, and I just realized that you can't see this. We'll just shove it behind the chat. So, we'll just undo that. The pressure at that elevation must be less. And it totally is. So, if you've ever been somewhere, like on a trip, and you had to stay somewhere that was a higher elevation, you may have gotten altitude sickness if you were dehydrated or tired or whatever. I have had this exactly once, and I thought I was going to pass out in the airport. It was real weird. I flew from Seattle to Denver to, I want to say I was going to like Iowa or something. I have a lot of friends in Iowa, and I have no idea why. Nothing against my friends, it's everything against Iowa. But I missed my flight, so I was real stressed out. I hadn't drank much water. I think I hadn't gotten much sleep that day. And I had a layover in Denver where I had to go to a hotel because I had missed my flight. I was like, did I explain that? Yeah. When I got off the plane, I was like, I felt like I was just going to collapse. And part of that is due to altitude sickness. If you're dehydrated, or your blood pressure is high or something like that, it causes crazy things to go on with your physiology. This is a real common thing that I've been told in like the Andes in is it the Andes? It's in Chile is where I'm thinking. That mountain range down along South America, because it's just so high up. if you go visit there and you abruptly change altitude, it can screw with your head. More likely, the increase in pressure that you have felt is if you've ever gone swimming in a swimming pool. So this is exaggerated over here. We're not going to be at the bottom of the ocean. But let's suppose that this is just a small pool of water. Then the pressure that you're feeling is going to be this plus the water that is pushing down on top of you too. Water is way heavier than air is, right? So the pressure that you feel underwater and I can't spell, so we'll do that. So the pressure increases at elevation below sea level. So pressure is a function of how much air is above you at any given time. If there's less because you went higher elevation, you're going to feel lower pressure. If you are below sea level, i.e. you're underground, or you are underwater, or you have something above you that is also pushing down on you, then the pressure that you will feel increases. This is an experiment you can do in a swimming pool. If you've ever been in like a 10-foot swimming pool and you've dived down to the bottom, at some depth, your ears start to hurt a lot. When I was a kid, I could dive all the way down to 10 feet. I don't think I could do 10 feet anymore as an adult. Probably kill my ears. But you definitely feel it. It hurts. And that's because of pressure. Your eardrums are not used to that. Likewise, if you're on an airplane, the pressure gradually gets lower because of just how leaks and stuff work. We're going to draw pictures of balloons when we come back tomorrow for lecture to describe some properties of things. But since there is reduced cabin pressure, just slightly, you feel that in your ears because your eardrums have air trapped behind them. And when that pressure on the inside of your eardrum does not equal the pressure on the outside, you get what feels like a bubble in your ears. And then you have to chew gum or eat something in order for the pressure to alleviate and equalize. Once it equalizes, your ear goes back to normal and you can hear again. Then when the airplane lands, you go through the same issue, right? Now the pressure on the outside of your eardrum is higher than the pressure on the inside because you've equilibrated to the lower pressure at a higher altitude. So pressure is just a function of elevation and air amount over you. And I feel like that's really all that we have time for. So we're going to come back and define pressure in terms of numbers a little bit more tomorrow. But really, the unit that we're going to care about is the atmosphere. And just remember that 1 atmosphere is the pressure that you feel on the surface of the planet. But very importantly, you have to be at sea level. If you're not at sea level, it's going to be more or less depending on which direction you go. If you go up from sea level, then you feel less pressure. And if you go down below sea level, you feel more. All right. I do want to thank everybody for coming out to the lecture. We are done with Chapter 6, which means that I'm going to go put the quiz up. I'm going to do that later today at 4:30 because I have to prepare for my other class. But otherwise, upcoming assignments are just lab worksheet number 3, which is due this week. Make sure that you get that done by either tomorrow or Wednesday before it closes. Okay. I can't think of anything else that I want to do, so I'm going to hit this button to start this ominous music. That means I'm about to go. Have a wonderful day, and I will see you tomorrow. We'll do more Chapter 7 then. Take care.